Hey dudes, it's Mr. Post, and on today's video we'll be checking out a very complicated topic known as molecular polarity. And the goal for you today is simply to leave this lesson saying, can I look at any molecule and classify it as either polar or nonpolar? Molecules will all fall within this range of either being polar or nonpolar, and there's actually varying degrees to which you are polar. The gist of today's video is not really the varying degrees in which one is more polar than another, but rather simply can you look just at a molecule and say, is it polar or nonpolar, simply based upon its shape. So, molecular polarity does depend upon two things: the symmetry of the shape of the molecule and also the polarity of the bond itself. Now, just so we're crystal clear, this here is a bond, that's a bond, and that's a bond. There are three covalent bonds in that molecule I've identified. The whole entire molecule, though, is what we're talking about today. This is molecular polarity, not bond polarity. So we're going to be focusing on the whole entire molecule and the symmetry of that shape. Nonpolar molecules are molecules that do not have positive and negative sides. Like a good example here, like this is the whole entire molecule. It's a trigonal planar, and let's just say it's like BF3, boron trifluoride. You know, one thing you might see with boron trifluoride is that all these fluorines are actually negative. And although they're actually negative and the middle might be positive, I do not have a positive and negative side. I don't have a dipole. When the middle is positive, what I end up with here is a negative end. And that is not a pole. A pole has to be something where one side is totally positive and one side is totally negative. So nonpolar molecules tend to be symmetrical. All right, this trigonal planar shape is symmetrical. It's the same on all sides. On this side, it's a white molecule bonded to a white molecule. This side, a white molecule bonded to a white molecule. And likewise, this side, this is a side, a white molecule bonded to a white molecule, for the sake of explaining this. Polar molecules, though, they do have a plus and a minus side. One side of the whole molecule is positive, and one side of the whole molecule is negative. And we tend to say their shape is asymmetrical. It is not the same all over. The one example of an asymmetrical molecule here is the bent molecule. Bent molecules are asymmetrical. You'll notice that the bottom here is different than the top. And because of that, it gives it a polar nature, where this side could be perhaps positive and this side could be perhaps negative. It doesn't have to be that way, though. The causes of polarity are, one, the asymmetrical shape. I want you to know that whenever you see a bent molecule, it is polar. Anytime you do a Lewis dot structure and you do a throwdown of the shape and it's bent, it is a polar molecule. Anytime you see trigonal pyramidal, it is also a polar molecule too. What you'll notice, the characteristics of these molecules, is that they have unshared electrons on their central atom, and that causes the valence shell electrons to bend away. These are characteristics of polar molecules. Also, polar bonds can contribute to a molecule being polar. It does not always have to have polar bonds, but it can. One of the things I want to get across is that just because they have a shape such as tetrahedral, and tetrahedral can lend itself to be a symmetrical shape, in this case it is asymmetrical because this other element over here is different than the other three. So I can have asymmetrical due to my shape of bent or pyramidal, and also asymmetrical when I do have a symmetrical shape, but the outside is different somewhere. And we'll go over examples of all of these. So, what I want you to leave here with now is knowing that anytime I have a tetrahedral, a linear, and a trigonal planar shape, they can either be polar or nonpolar. And that depends upon the symmetry within that molecule. Are all the ends of the molecule the same, or is one of them different? Bent and pyramidal are always polar. And they always have an asymmetrical shape that will lend to that polarity. Some examples of symmetrical and asymmetrical. This is a symmetrical tetrahedral shape, which would be considered a nonpolar molecule. And this is an asymmetrical tetrahedral shape. Because I have asymmetry here, it is not the same on all sides. It is considered a polar molecule. Here we have trigonal planar, and here we have trigonal pyramidal. And I want to say the sides are these. These are the sides, all right? The sides are white connecting to white, connecting to white, connecting to white. This is a middle. The middle is not a side, unless the middle is elevated. And that's what we have here. In trigonal pyramidal, the middle is actually an elevated structure here, where I do have sides of my molecule if you were to build it like this molecular model kit is. So symmetrical leads to nonpolar molecules. Asymmetrical, to varying degrees, it will always be polar. Once again, what's the main difference here? The trigonal planar lacks an extra pair of electrons because it's a group 3 element. Trigonal pyramidal will have that extra pair of electrons on the central atom, which will cause other electrons to bend downward and this to be elevated upwards. Now the middle does have a polarity that is different than the other sides. How about this shape here, guys? We have something like CO2 versus something like H2O. Once again, this is linear. It is the same on the sides. These sides will contribute to a negative, perhaps, charge, and have a negative end. That is not a pole. This here, though, gives me a one side of the molecule can be perhaps positive and the other side negative, and that would lead to a symmetry and a pole being created. A pole where one side is positive and one side is negative. What's the main difference between these two molecules? Well, they both have 3 atoms, but this one's got that extra pair of electrons that carbon dioxide does not have on the central atom. Carbon dioxide on the central atom lacks that, therefore it leads to a symmetrical shape going across in linear. Okay, guys, here's where it comes down to. I want you to start trying these examples. Are these examples of polar or nonpolar molecules? Here we're looking at any one of these. It could be carbon tetrafluoride, it could be methane, silicon tetrafluoride. The thing is, they're both group 4 elements. They'll be looking like this in the Lewis dot structure, and all the Lewis dot structures have this shape. Is this a symmetrical shape, or is it asymmetrical shape? That's the first thing you have to ask yourself. All right, take 2 seconds, guys. Answer the questions from now on. Take a shot at it. Press pause. I'm coming back with the answer. This is a nonpolar molecule. It's symmetrical all over the place. Every single outside is identical to the other outside. Therefore, it is symmetrical and nonpolar. BF3, boron trifluoride. The bonds on these are very, very polar, but is the molecule polar? In this case, the molecule is nonpolar because it is a symmetrical shape. No matter how you spin this, it's always going to look the same. Let's check this out, guys. Either of the compounds here, NF3 or PF3, whatever one you want to use, they both have the same Lewis dot structure because they're both group 5 or 15 elements. I want you to look at this down here. Is this a symmetrical shape or an asymmetrical shape, classified as polar or nonpolar? This is a polar molecule. Trigonal pyramidal is always going to be a polar molecule. In this case, I have differences. These 3 are going to be different than the very top one here. Therefore, that's going to lend me to having a polar molecule. What's going on with H2O or H2S? Well, either one you choose is going to be a polar molecule. I've already said that bent structure is a polar molecule, so therefore, you already know coming in, when you see bent, it is polar. CO2, what's going on? Well, it forms in the shape of linear. Linear is an example where it could be either polar or nonpolar. But because of my N's, the O's are identical, in this case for silicon dioxide also, if the N's are identical, therefore the molecule is going to be nonpolar. There is no poles present here. Nitrogen is a great example of a linear molecule that is the same on both sides. When you're same on both sides, you're going to be nonpolar. Carbon tetrafluoride. This is a tetrahedral shape, and you'll notice that the exterior is all the same. Each one of these is a fluorine, that's a fluorine, that's a fluorine. So really, if fluorine is going to take on a negative charge due to its electronegativity, which it will, I want you to notice this. You have negatives all over the place on the outside. And yeah, the middle is plus, but the sides are kind of what matters. These sides are all going to be negative sides, negative charges. Therefore, although you have very polar bonds, you have a nonpolar molecule. The example here is fluoromethane or methyl fluoride. Take a look at it, guys. Please decide whether or not it's polar or nonpolar. Well, if these three atoms on the sides are hydrogen and this one's a fluorine, clearly this is asymmetrical. This is not the same threat anymore. I have 3 H's, 1 F. Now, this is definitely going to be a polar molecule. How about oxygen? Well, oxygen should be pretty easy, guys. It's linear, and it can go either way. It can either be nonpolar or it can be polar. The fact that I have the same atom on both sides, though, kind of lends me to thinking, yes, this is going to be a nonpolar molecule. What about hydrogen monofluoride, also known as hydrogen fluoride? How do you take this one? It is linear. Is it symmetrical or is it asymmetrical? Well, checking this out, guys, you'll notice that if I split the atom in half, or the molecule in half, I have one side that's fluorine and one side that's hydrogen. They're not the same. They're not symmetrical. This would be considered actually a very, very polar molecule. What do you think about oxygen difluoride? Oxygen difluoride happens to be a polar molecule. It's a polar molecule primarily because of its bent shape. You have two unshared pairs of electrons up here that are going to cause the structure to be repelled downwards, and as it is repelled downwards, now I have a bottom half that is different than the top half, and that causes a polar molecule. So here we have polar. This one shouldn't be too hard. I think everyone you've seen so far, that's been N2O2. This is F2. Fluorine is the name of the molecule. It is the same on both sides. It is almost like a mirror image here, guys. That's total symmetry. Symmetrical molecules are nonpolar. Check out the picture here. This is a molecular model of ethanol. And this is the Lewis dot structure down here. So if you look at the Lewis dot structure, you see I have this OH ending. OH endings always indicate alcohol group. An alcohol group was attached to ethane. And in this case, if we're keying on this over here, just looking at that, do you think this picture shows a symmetrical molecule? So what I want to really demonstrate is just by looking at the symmetry of the molecule, you can predict its polarity. You're not going to be able to tell how polar it is, but you will be able to tell that it is polar. This is an example of clearly of a polar molecule. That one side is clearly different than the other side. So ethanol is a polar molecule. This is a Lewis dot structure of cyclopentane. If you look at the picture here, it kind of makes it a little easier to see perhaps, but it's the same. Every carbon is attached to two hydrogens and also attached to two carbons. No matter which one you look at, it's identical. You know, this one down here is the same as this one over here. And because it has that symmetry, cyclopentane is nonpolar. But on the next slide, I'm going to make it polar. I added the alcohol group, the OH, to one of the carbons. And in doing so, I have altered the symmetry. Now this is asymmetrical, and this will cause polarity with my molecule. This cyclopentanol is a polar molecule. What about ethene? That's actually a linear molecule. It might be difficult to tell, but it's actually linear. It's not bending at all. It's a straight line going across. All right, well, now you have a straight line going across. Are the sides the same? Do I have the same symmetry on both sides? And the answer is yes. This is a nonpolar molecule. So once again, guys, the goal today was to discuss molecular polarity, to introduce you to the idea that the molecules can be polar and nonpolar, but what I really wanted to key in on was that molecular polarity can primarily be determined by the symmetry of the shape. That is the number one thing. How polar it is, though, is going to be determined by the bond polarities. You have to be careful there. The bond polarity is very important, although I don't cover here. The symmetry will tell you whether or not it's polar or not. The bond polarity can really tell you how polar it is and how big of a dipole moment that has. All right, guys. Well, thanks a lot for tuning in. I hope it was helpful. Be good.